So you've made it to the end of Unit 3, and our last lesson in this unit will be talking about inverse trig functions. And not only that, we're going to differentiate these inverse trig functions. And that's why in our last lesson we did derivatives of inverse functions. Now remember, none of the 6 basic trig functions is actually one-to-one. One-to-one meaning for each x value there's only one y value, right? Or for each y value there's also only one x value. Remember? Look at sign. Whee, right? Not one-to-one because multiple values, multiple x values for the same y value. So really then none of them will have an inverse. So why are we doing this? Well, hold on. We can use domain restrictions to make sure that the trig functions actually do become one-to-one, so that they can have inverses. And in this course, we will only deal with the inverse trig functions for sine, cosine, and tangent. Whew, thank goodness we don't have to do cosecant, secant, and cotangent. Now, remember inverse trig functions, the notation for it is arc sine of x, or sometimes people might use this notation, sine -1 of x, but people don't like that sometimes because they confuse that with reciprocal, and that's not good. So arc sine is the preferred method of doing it, but once again sine -1x is the same. Just knowing that, of course, if I wanted to solve for x, I would have to take sine on both sides. That's why sometimes inverse trig functions is defined as this, x equals the sine of y. Okay? Now, I drew the sine graph up top here. I think if I were to ask you to actually graph out arc sine, would you be able to do that? Well, remember, if I did sine, I'm going to use example number 1 here. If I were to do the sine graph, 0, and then like this, right? Whee! So, if I asked you to do the inverse, you're going to reflect this in this line. So you hopefully will see some sort of graph like this, right? And then maybe over here like this, So ultimately now, if I were just to look at the graph of the arc sine, you should see something that looks like this. And notice how when we limit the domain values to be -1 and 1, then the corresponding range values for y for the arc sine graph is -π/2 to π/2. Okay? And once again, if you think about what I did there, I just did this graph, up to 1, right? And then -1 down to there. So this is the sine graph, and that corresponds to this inverse sine graph here. Okay? I'd like you to try to do the same thing for cosine then, and also for tangent. And I want you to try that yourself. So once again, cosine starts at 1 to -1, right? And notice in this case, the domain goes from 0 to pi. What happened there? Arg. Okay. So notice for cosine, graph starts at 1 to -1. The domain is 0 to pi, so that's cosine. So therefore, the domain values for arc cos, which would be the inverse, is of course -1 to 1, and the range values from 0 to pi. And if you were to do this, I hope you can see something like this as your graph. Okay. And then finally tangent. Remember tangent has those asymptotes. And at -π/2 and pi/2. That's why the range values are like this, and the domain values will be everything. So you're just taking this and reflecting it. Your asymptotes are now horizontal. And hopefully you can see something that looks like this. Okay. These are the 3 graphs of the inverse trig functions. Alright? So, moving on the next page, hopefully you can see that there's a geometric representation of the range values. Once again, the range values for each of the inverse. So arc sine and arc tangent have the same range values from -π/2 to pi/2, except of course arc tangent, they are empty dots here because they're asymptotes, yet for arcsine they are solid dots. And then cosine is a different one. It goes from 0 to pi, so that's why I drew it like that. Okay? If this helps you memorize the the range values, by all means go ahead. If not, just memorize them yourself some other way. Okay? So, remember that the answer to an inverse trig problem must fall in the correct range, and that there is actually only one answer now, not multiple answers, just one. Okay? So, looking at example number 2. Here we go. What's sine of negative pi over 6? Well, hopefully you remember that these values from our pre-calculus days. Sine is down here. Hopefully you can see you got a nice right angle triangle. It's a 3069 right angle triangle or a pi over 6 one. Root 3, 2, and because it's in quadrant 4, this is negative 1. So yes, this answer is just negative half. Sine 7 pi over 6. Well, where's that once again? So 7 pi over 6 would be in quadrant 3. Notice the triangle you're creating is this. Negative root 3, negative 1, and also 2. So the sine value, once again, is y over r, also negative 1/2. And sine 11 pi over 6, that's going around like that. You're actually getting the same answer as part A, the same triangle, root 3, negative 1, 2. So this answer is also negative 1/2. So now, if I asked you what is the arcsine of negative 1/2, you could say this is going backwards, or the inverse, so this should be 11 pi over 6, 7 pi over 6, and negative pi over 6, right? All three of them. Wait. Like what I just said up here, arcsine now has a range from negative pi over 2 to pi over 6 only. So there's only going to be one correct answer. So which one is the correct answer? Negative pi over 6. Only one, okay? Only one answer. Alright. So knowing this now, can you try example number 3? I want you to answer these questions without a calculator, okay? So this is where you need to know your special angles. So arctan of 1, really what I'm saying is what angle produces a ratio for tangent being equal to 1? And if you said pi over 4, you are right. Arc cos of negative 1, once again, what angle for cosine produces this ratio of negative 1? So think about where negative 1 is. Cosine graph, negative 1 comma 0. Yeah. If you said pi, you are correct. Inverse sine of negative root 3 pi over 2. Negative root 3 pi over 2. Inverse sine. Any idea here? So once again, I gave you the ratio, negative 3 pi over 2. It's going to be in quadrant 4. The y value is negative root 3, 2, 1. What is this going to be? Wrong way. Remember, I have to go clockwise, which means my answer is negative. So we said negative pi over 3. I'm happy. And how about arcsine of 2? So you're saying what angle gives me a sine ratio of 2? And if you said, I have no idea, you are correct, because the sine range values go from only negative 1 to 1. So arcsine of 2, no way. The domain here was only values that are between negative 1 and 1, not in the domain, no value. Okay? Alright, example number 4 is pretty straightforward. You just have to do that with your calculator, so bring out your calculator and punch it in. Remind yourself that when you're dealing with tangents, sines, and cosines, you should be in radian mode. My calculator is taking a while to come up. Hello, calculator. Well then, while you wait for my calculator, why don't you just punch it in yourself, right? So here's my calculator. Ooh, lots of lag. That's not good. Now you see 2. Well, I see 3. That's not a good sign. But anyways, mode, yes, radian, arc sine, that's inverse sine, and then just type in 0.304. Good, so 0.304, and the calculator already has those range and all those values set in there, so that's good. Let's turn this on again. Arc tangent this time, so second function tangent of -5/2, and lo and behold, -1.190. Remember, AP, 3 decimal places, please. Alright. So, see if you can do number 5 now. Now I have inverse functions and functions back to back. Inverse back to back, what do you get? You just get what you started. That's right, so √3/2. Hey, tan and arctan, you just get what you started. 3, good. Arc cosine cos, you just get what you started with. Pi/3. Arc sine and sine, you get what you started with. 11 pi/6. Hold on. Hold on. Hold on. I thought that arc sine had range values between... Uh-oh. Got too excited there. The range values are between what? -pi/2 and pi/2. But what? This is 11 pi/6. Uh-oh. So what is the equivalent value? 11 pi/6. That's in the fourth quadrant here, right? Yeah. But what is the equivalent coterminal angle? That's negative in this domain, or this range. Yeah, if you said -pi/6, that is correct. So this one here, be careful, be careful. It's not 11 pi/6, but -pi/6. Tricky, tricky, tricky. Okay? So once again, we're not really doing any calculus right now. We're just still trying to show you what inverse trig functions look like. You can actually solve for the inverse trig functions as well to get rid of the arc sine. What do? Well, we take sine on both sides, right? Sine of this and sine of that. And so if we take the sine and arc sine, yes, we're left with just x² - 3. What is sine pi/2 though? Yeah, that's actually a value. That's equal to 1, right? So now we have x² - 3 equals to 1, or x² equals to 4, and thus x equals to ±2. Okay. Moving on. Number 7 and 8 are going to help you with number 9, which is really what we're going to be focusing on, because this is a calculus course, so we really want to find some derivatives. But before we do that, let's see if you can actually answer questions 7 and 8. So now if I said x is equal to arc cos of 2/5, from this piece of information, can you figure out the tangent of that value of x? Now x, once again, is an angle. Okay, so when I say x equals to arc cosine of 2/5, I'm saying the angle. So what angle, when I take cosine of it, gives me the ratio of 2/5. So think about it as a picture. What angle, when I find the angle, when I take the cosine of the angle, gives me a ratio of 2/5. Well, cosine is defined as x/r. So x is 2. R must be √5. And then because this is a right angle triangle, we can then figure out the missing side length here. I'll call it y. And if you said y equals to 1, I'm happy. And then why did I do that? Well, what's tangent of x then? Tangent is defined as y/x, right? The ratio of the y coordinate with the x. So there you have it. It's just 1/2. Okay. Be careful with this x and x. Yes, I'm sorry. This x is the angle. This x over here in blue is the x coordinate. My fault. Okay. A little bit messy with the notation. Okay, how about this next one then? Given that y equals arc sine of x, find cosine of y. So in this case now, what I'm saying is y is the angle. So if I were to draw a triangle, y is my angle. Okay, y is the angle. And then here's arc sine is x. What does that mean? Well, another way of writing this would be what? The sine of angle y equals to x. And then as a ratio, this would be x over 1. Then the ratio of sine is the opposite side, which is this one, opposite the angle, that's x. And the hypotenuse is 1. And knowing that, then, how can I go ahead and find the missing side here? Yeah, using Pythagoras, this is just the square root of 1 minus x squared. So, what is cosine of y then? Well, cosine of y is defined as the adjacent side, which is just the square root of 1 minus root x, and hypotenuse, which is 1. So we don't have to really divide that by 1, but if you wanted to, that's fine. I prefer if you just write it as this. Okay, so you're like, why did we do that? Who cares? Now you care, because I want you to do example number 9. Okay? Number 9 says, can you find the derivative of arc sine of x? And I'm going to use the work from example 8 to help you. Well, if I want to find the derivative of arc sine of x, maybe I want to just rewrite this as y equals to arc sine of x first. Okay? And I want to find the derivative of this. I don't like this arc sine business. I don't know any derivatives for arc sine. I do know the derivative for sine though, right? So why don't I just try to get rid of this arc sine? And I'll get rid of the arc sine by taking sine on both sides. Because if you do that, look, sine y equals to what's sine of arc sine of x? Yeah, just x. Well, this is nice, because I know the derivative of sine. Do you? I hope you remember that the derivative of sine is cosine of y. And if you said this is equal to 1, you are almost right. I'm asking d dx, which means take the derivative with respect to x. Y is implicitly, oh, did you hear me say that? Implicitly a function of x. Oh, that beautiful sound of the extra little bit. Y prime. Don't forget y prime. So y prime in this case is just 1 over cosine of y. And you're like, I still don't understand how I used it work from example number 8. Well, didn't I ask you to find cosine of y? In this case, when y equals arc sine of x? Well, make that substitution now, because that's just equal to the square root of 1 minus x squared. And now you have the derivative of arc sine in terms of x. And this lovely chart underneath is exactly where this came from. Ta-da! You can do the same thing for arc cos and arc tangent, and you'll get those 3 functions. Okay? So I'm not going to prove these to you, but you can do it yourself, or you look in the textbook, or whatever else, look online. But they are very similar to what I just did in example number 9. Okay? On the right hand side here are all the chain rule versions. So instead of having x as a variable, now we have u as a function. And once again, you replace x with u, and don't forget an extra little bit. That extra bit is that u prime that you see. U prime, u prime, u prime. Okay? So let's quickly do 3 examples, and then I'll call it a day. And of course, like I always say, practice, practice, practice. So, g of y is arctangent 2y minus 1. I'm going to ask you to differentiate, this time in terms of y. So the derivative of arctangent is just 1 over 1 plus whatever you have there, all squared. But don't forget the extra little bit, which is the derivative of the inside function. In this case, the derivative of 2y minus 1 gets an extra factor of 2. So if you left it like this, 2 over 1 plus 2y minus 1 all squared, I will be happy. Alright, be careful here with arc sine of root x. That's just, of course, x to the 1/2. So its derivative here is 1 over the square root of 1 minus x, which is in this case root x all squared. But don't forget there's an extra little bit, which is the derivative of the inside function, 1/2 x to the negative 1/2. And so if I wanted to simplify this expression, I could put the 1/2 in the bottom. I have a root 1 minus x, like this, because root x squared is just x, and then this x to the negative 1/2 just becomes another square root of x in the denominator. Okay? Ooh, highlighter. I don't know how it changed by itself. Strange. Okay, and finally, number 12. This notation, cos -1, that just is the same thing as arc cos of the natural log of t. Ooh, getting nasty now. H prime, the derivative of arc cos is -1 over the square root of 1 minus x. In this case, x would be like ln t all squared. And don't forget that extra little bit. And that extra little bit, of course, is the derivative of ln t. What is the derivative of ln t? Yeah, 1 over t. So, -1 over t, or I'll say something like this, -1 over t root 1 minus ln t all squared. That is your derivative. Done! Okay? Once again, box, unfortunately, memorized. I think you should be actually putting together a little like formula sheet here. I've seen a lot of boxes lately with all these different derivatives. Yes, you will need to know all these derivatives as we move forward. The next part in Unit 4, it's time to apply. And we're going to apply all these derivative rules to problems. Alright. Enjoy the work. See you back here for Unit 4.